our student presentations. And it looks like we have some of our presenters here, Abhishek, Kumar. We have Andrew Goost. I hope I'm saying that correctly.
Guest.
Yes.
At a hotel.
Thank you so much. And we'll be playing a video and then he'll be here for questions afterwards. We have plenty of time during the session. Andrew, do you have anything you would like to say or a little introduction about yourself before we start the video?
Sure. I'm a third-year computer science student. I'll be graduating this summer. I have an emphasis in artificial intelligence. I'm an undergrad research assistant at the Center for Geospatial Research here, and I prepared a PowerPoint presenting our AR activities at our disruptive geospatial lab. I'm excited to showcase it. And that's me.
Awesome. Thank you, Andrew. My name is Caroline Narron. I'm going to be the moderator for this event. We really appreciate all of you being here. And yeah, so we'll go ahead and get started, Andrew, with your video. I'm going to start to play it now, and then after we'll have time for questions for you.
Awesome.
Let's see.
Today, my name is Andrew Guest, and I'm presenting augmented reality activities at the Center for Geospatial Research. We are part of the Department of Geography, and I'll be showcasing the work done at our Disruptive Geospatial Technologies Lab, or Digital. The underlying system of our lab is the 3DIG system, 3D Immersion and Geovisualization System. These four components, image acquisition, virtual reality, augmented and mixed reality, video displays, all work together to produce geospatial data. For example, a drone can capture buildings using structure for motion, create a 3D representation of those buildings, and display it in an augmented or mixed reality environment. It could also be displayed in a virtual reality environment, and it obviously can be displayed on displays. This shows interconnectability of this 3DIG system and the brilliance of it. Speaking of augmented reality, I would like to talk about AR Globe. Our goal of this project is to provide interactive globes in an AR environment. We would like to present multiple concepts in geography with this application. For example, we can display the physical Earth, sea temperature of the Earth, and other data that may be helpful to represent. In this day and age, infection rate would be a very helpful statistic to display. Here's the application being run on an iPad. We can also select different displays of the Earth based on month. Currently, we are working on porting this project from Apple-based to be supported by both Android and Apple using the Unity game engine. The photo on the right is AR Globe in a Unity environment. And also here is the sea surface temperatures in AR Globe. Moving on to the next AR project is the Augmented Reality Sandbox. The Sandbox works by having a capture device above a sandbox. We use an Xbox Connect. It generates an elevation map from the sandbox and then projects features extracted from the elevation map onto the sandbox. The sandbox is very helpful for research as it is near real time and used for many what-if scenarios. Here are some more photos. We enhance the augmented and mixed reality experience by adding virtual elements to the sandbox, such as contour lines or altitude lines and liquids. Check out this animation of the sandbox in action. As you see here, he's moving the sand around and he's changing the contour. And then he puts his hand over the sandbox and it starts raining. And you can see the liquid. How cool is that? Here's a project that I started working on when I first arrived here at CGR. My goal is to integrate a wind simulator into the tangible sandbox. The simulator extracts an elevation model from the sandbox or from user reference, converts the model to 3D terrain, runs a simulation, and then drapes the wind vectors over the sandbox. The simulator can provide a simulation in just a few minutes, which is very impressive for a simulator. Simulation is a complex problem, and weather simulations are usually done on supercomputers. Here's a graphical example. As you can see, here's the sandbox and the cameras, and it's going to pull the data, run it through the computer. Computer does its simulation, its magic here, and then the wind vectors get draped right on over it. Here's a maximized photo of the Mount St. Helens simulation with a reference photo of Mount St. Helens. See? And this is after the eruption. So this is a physical photo. Here's a simulation. As you can see, it's wind vectors go around the peaks of the mountain, or the volcano, I mean. Here are some more simulations. The photo on the left is a simulation from a hill in Wyoming. The photo on the right is a simulation of Athens, Georgia. Right here, there's a river, and you can see the wind kind of flows through the river as it's a gap in the hill, you know? We can integrate all our technologies to create a comprehensive AR and VR experience. We can use a drone to recreate buildings into a 3D object, represent them in a 3D world, make that 3D world compatible with VR. Pretty cool, huh? I'll be going into our other projects. The tangible landscape allows us to incorporate many activities for demonstrations of concepts and processes in the earth sciences. For example, an activity would be guided terrain building, where the landscape would guide you to build terrain using colors. For example, the color white means the terrain is on level, no more sand needs to be added or removed. I've already hinted about some of the 3D reconstruction efforts. Cobb's World is a project used to reconstruct some of the historic buildings in Athens, one of them being the Cobb House. We fly a drone over the buildings to capture the structures from motion into a detailed 3D object. Our goal is to represent the buildings as it would have been seen in the 1850s. So these blue squares here is the path of the drone. And we actually fly over it multiple times since we need to capture the angles of both buildings. So we would go this way and then this way. Because if you only flew a drone above the buildings, you couldn't get the walls. And obviously the structures and 3D models that are produced by the drone are very detailed, as you can see here. And this statue, in the grand scheme of things, is pretty small. It's about the size, it's about over here. We are collaborating with the Department of Psychology here at UGA to merge geovisualization and digital technologies with the science of human psychology. The acrophobia simulation project is essentially a game where the participant is in a VR world and has to fight their fear of acrophobia. You know, this could be a tightrope, it could be a bridge, etc. As you can see here, it's basically a game. Another project that the collaboration has worked on is simulating the different levels of color blindness here. So this is normal, and these are the other levels of color blindness here. Let's go into some of the applications that our lab offers. Here's the statistics of our lab. We have over 6,000 individual interactions, 55 courses and sessions we have participated in, 13 events, and 22 student developers. Here's an image of our assistant director, Sergio, showcasing the AR globe in the classroom. Here's a showcase of the Sandbox to a group of students learning for their geography class. It serves as a great learning aid to students. Believe it or not, this is how I first met the center. Overall, one of the biggest missions here is to enhance teaching and learning with disruptive technology. So we're using, virtual reality in the classroom. We have the Sandbox pulled into the science library, and then for service here with also the virtual reality headset here. Pretty cool, huh? We would like to thank the Center for Teaching and Learning at the University of Georgia as they have funded the lab. Thank you all for watching this presentation for GIS Day 2020. I hope you all enjoyed the presentation. Please visit our website if you wish to learn more. And also let me know if you have any questions. Have a good one. Bye.
Great job. Thank you, Andrew. Does anybody have any questions for him? Or Andrew, do you have any comments to add?
Nope, I'm just taking questions.
Sure. Abhishek, I think I saw you.
Yeah, so I just wanted to know that simulation you showed for eruption. There was an eruption going on. So that simulation is for elevation, or what was that simulation? Because I didn't see any scale bar, there.
Sure.
On any, yeah.
So that map is an elevation map. So the brighter colors, higher elevation, darker colors, lower elevation. And that's what we use for the map. And then we draped the wind vectors over the map. Does that answer your question?
Yeah, what data did you use for elevation, like simulation there?
So basically our Kinect cameras capture the elevation model. Basically, it's the first thing it does since it's a depth camera. So the depth camera converts the data, and then I take the elevation map and then run it through a simulator. Or actually, no, I run the elevation map through a mesher, which converts the elevation map to a 3D model. And then the 3D model has a simulation ran over it. And then I drape the results of simulation onto the elevation map.
Yeah, thank you.
Yeah, absolutely.
Awesome. It looks like we have a question in the chat. Austin asks, what are some of the major challenges integrating the wind simulations to the sandbox?
Actually, coronavirus is the biggest challenge. It's actually, we can't actually get to the center right now, and the sandbox is kind of a hot issue with the coronavirus because you don't want people touching in it and spreading the virus. So the hardest part is actually merging them together. So basically the simulator is ready to be integrated in the sandbox. You just have to replace the user input with the camera. So that is the biggest challenge, is the coronavirus.
Awesome. Thank you for sharing.
Mm-hmm.
Any other questions from the audience?
I do have one comment. Well, nicely done, Andrew. Yeah, thank you for that.
Thank you.
One thing that perhaps could be, I'm getting some feedback. I don't know why. Well, Abhishek. So in terms of input, it is correct. It comes from the sandbox, but you also have an option that is you bring a digital elevation model that can come from USGS, for instance. So
yeah, that's what I thought actually. Like, you know, it's from USGS.
Right. So it accepts. This runs on top of GRASS. So the idea here, what this is doing is collecting data from the sandbox and sending the data to GRASS GIS. And there's some processing there, and also OpenFOAM for the modeling side of it. And since it's GIS data, it's flexible enough to accept data coming from the sandbox or data coming from other sources that can be USGS or whatever. You provide your own data.
Yeah, because I saw, like, you know, that mountain area, so you are not flying there, right? So the data definitely coming from somewhere else.
That's correct.
Yeah.
Andrew, could you, we are not taking too much time, could you mention the idea there, the before and after?
Before and after of the sandbox?
The eruption?
Oh yeah, so basically, so we the eruption obviously changed the wind vectors of the area because, you know, the volcano before the eruption looked like a complete circle. Well, now, you know, instead of flowing around, it's, you know, it's completely altered the wind fields at the top. I think I got that.
And does that affect like how planes fly nearby, or is it just like environmental changes for Mount St. Helens? So I'm assuming that wind sometimes goes into the cavern.
Yeah, so I mean, I don't think planes would fly over Mount St. Helens because of how high it is. So I don't think it would affect like planes specifically, but it would affect the weather in that region, like in terms of like a micro scale.
Mm-hmm. Boundary layer level.
Yeah.
Mm-hmm.
Awesome. Very, very cool.
Thank you.
Okay, I guess we're right on track time-wise, so we're gonna move on to our next presenter. I'd like to invite Inhye Kong, a PhD student in the Department of Geography, or sorry, PhD candidate in the Department of Geography, to present her work.
Awesome, thank you, Caroline. Hi everyone, my name is Inhye, and then I'm PhD candidate. I just got promoted from candidate this spring, in the middle of pandemic. And then I've been working on my dissertation, and then this is only a small part of one of the manuscript that I'm working on. So let me share the screen real quick. So, oh no, not the data. Let me go back to the very first. So I've been working on geodemographics of national park visitors, and then this is only a very first part of this manuscript, and then I thought the result is pretty interesting, and then somehow maybe interest some of you, so I'd like to share some of the results that I had. So when we first defined what geodemographics is, so this is the study of where people are. So when we are talking about geodemographics in this kind of tourism perspective, it means that like to monitor where the visitors are coming from, and then like where are their homes, and then how far they physically travel. So this is what the geodemographics is about. And we, as a geographer in geography department, we are so much aware of the first law of geography. So everything is related to everything else, but near things are more related to than distant things. So this is the basis of the distance decay. So the interactions, for example, the visitation, it is related to like the distance. So like this, when the distance is like far away from the core, so that means that there'll be less and less interactions. And also the Hub's gravity model, this is a way to measure the visitation in more like business wise, but they also follow the concept of the first law of geography. So my question was about, does this national park tourism follow the first law of geography? So if we are just talking about the local park or just state park, we can intuitively assume that like this distance decay may influence a lot in this visitation, but national parks are more of iconic tourist destination. So we have little information about the visitors in national park because they really don't keep track on everyone's hometown and then like how far they're traveling. So they are not so much of information about this. And when we are talking about the geodemographics for visitor management, in previous studies, many case studies have talked about how the experience of local, domestic, and international visitor can vary. So this is based on assumption that like people of different cultural background may have different place familiarity, so they may influence this place affinity and attachment, so that it will result in different experience and satisfaction. And then this experience and satisfaction is really important for tourism management. So that's why we are talking about this issue. And then when we are talking about the locals, that means that the local people are assumed to visit the destination more frequently, and then they have more special feelings for their destination. And when previous studies, when they are defining the locals, they did some surveys. And then when we are taking the survey, we can just ask directly, like, are you local or not? This is how previous studies has been done. And then some other studies, they defined this like local and non-local based on this specific distance. So when you are living in, for example, like 1 kilometers from the destination, then you're local, and then otherwise you're non-local. But I want to like really make sure that like where is this geographic boundaries of local area, and then I don't think this like the boundary will be the same for every like national park. So I wanted to make sure that like, are we really like having this kind of like definition, or is there any physical threshold in terms of the locals? So the question is like, does national park visitors follow the first law of geography? And then following question is about, does national park have identical distance threshold for the locals? If it doesn't, how are the threshold different? So I collected the data from at least 8 national parks. They are not like exactly following the visitation ranks, but I also considered the land cover of these national parks. So it should be forest dominant terrestrial national park. And then like I also considered the geographic distribution because so many popular national parks are just in the West. So these are 8 national parks that I collected data. I missed some data here. And then I collected these online tourism reviews from TripAdvisor because they not only have these reviews that I'm going to use in later in my study, but they also have these home locations. So when you check in the TripAdvisor, you can see the review like this, and then they have this profile picture, and then they specify their home location, and then this is totally voluntary. And I'm going to use this self-claimed home locations. And then I also had this GIS data from Open Data GIS. This is like the GIS data that is directly uploaded by NPS. So this is a reliable source. So the first analysis about to locate visitors' home. So I scraped these TripAdvisor home locations with R, with dynamic web scraping, and I'm not going to talk much about this scraping technology. And then like based on this home location, I had to transform this like place names into geolocations, which is like longitude and latitude. And then I used ggmap R package. I'm going to talk a little bit more about this. And then in ArcMap, I could like locate these geolocations in a map environment. So the ggmap is pretty kind of like really intuitive R package. So basically this is built upon Google geocoding API under Google Cloud Platform. So basically the package facilitate this transformation of place names into geolocation based on Google Map search. So like when you search a Google Map about a place name, they will take you to a certain location, and then like they have certain longitude and latitude, and then ggmap is just retrieving those geolocations based on Google Map platform. And to use this package, you need to register yourself. Of course, your credit card information should be put there. And then the free geocoding is only allowed like 40,000 a month. And then if you exceed this number, you are going to be charged. So if you are considering to use this package, just keep in mind that. And then I exported this geolocation, and then like I can bring it to ArcMap, and then I can put these geolocations on map. So you may all familiar with this process. And then this is the visitor's home who left the review in TripAdvisor in Yosemite National Park. And then you see that like there are some clusters of visitors around North California, and then on the East Coast area as well. And then there's some people from Florida, Georgia, and then this is how I identified the visitor's home. And I put this in histogram. So the x-axis is the distance, and then the y-axis is the frequency, the number of people. But I really cannot tell like where is the threshold of local. So it's really hard to just tell by this histogram. So I did more analysis. So I count the number of visitors by county level in ArcMap, and then I operated ordinary least square linear regression with the population by each county, and then the distance between the county and the destination national park. So this is based on the previous studies that like the number of visitors in national park may be influenced not only by the distance between their home and then the destination, but also the number of population in nearby cities that also have huge influence on the visitation. So that's why I put these two variables to run this linear regression. And then like once I have this equation and then the residual, I can put the residual in this optimized hotspot analysis so that like I can like draw the boundaries of this like people who are more interested in each national park. So I counted the number of people by this county level for Yosemite. And also I did the linear regression with the distance between this county and then the Yosemite, and then also the population by each county. And then the linear regression results that like there are more people who are interested in visiting this Yosemite National Park just around the Northern California area. So this is how I got the result. And then I got this like optimized hotspot result with the residual from the regression analysis. So that like I could draw like this red-ish area are the local areas for Yosemite. And I did this process for all 8 other national parks. And then for Acadia National Park, which is located in the Maine, so like in that area, there are more people interested in visiting Acadia around the New York and then Delaware area. So they have really long region of local area for Acadia. And then I have some interesting result for Great Smoky. So for Smoky Mountain, there are like people who are really interested in visiting Smoky Mountain around this radius. And then also there are some people from Florida, they also have like more interested in visiting Smoky, and then the Chicago area and also the north part of the West Coast area. There are also like slight hotspots there. So the conclusion is the first law of geography actually is true for national park visitors. And this is proven by the hotspots around the destination. And then also different national parks has different distance threshold of local area. So I'm going to use this result to do my next step. So so why the destinations have different distance threshold, and then how much of this visitor experience is different between local and non-local visitors. So that would be my next step. So thank you for listening. I am happy to answer if you have any questions.
Great job, Inhye. Thank you for sharing. That's really interesting, especially around the Great Smoky, how large that area is.
Yeah.
Especially because it is a relatively mountainous region, the Great Smokies. So it's there are people coming from multiple states, I'm assuming, in that whole area.
Yeah, for some other national park, like they only have really small hotspots around their destination, but for Smoky, it has really a large boundary, and at the same time, they have multiple hotspots. So that's really an interesting part, at least for me, yeah.
Does anyone have any questions for Inhye?
Can I ask a quick question? Can you hear me?
Sure.
So that was really interesting. One other question or just an alternative approach might be just doing a rate. So one of the questions is you've got participants and you have to normalize by population, which you did in your model, but then pulling in the residuals just makes it kind of several steps long. I'm wondering if you thought about, or if you did, just doing the rate per county and then just looking at hotspots for that to see if you get a similar kind of a map.
Rate, you mean the
reviews per 10,000 people or something like
that? Yeah. I've never thought about that thing. Thanks for your comment. I'll definitely check on that.
Yeah, it might just be a little more straightforward, and I think you'd end up with something very similar.
Yeah, thank you.
I had a quick question. What were the dates of the reviews that you studied?
So the date that was from the very first really ancient review from the reviews by 2020 February, because I just excluded all the reviews since this March because it is somehow influenced by COVID. And then I was concerned that like their experience may have been a little bit, I don't know, there may be some change of their intention to visit or their experience may be different. So I thought that could influence my analysis in next step. So that's probably from like 2012 to this February.
Awesome, very, very cool. Thank you for sharing. Does anyone else have any questions for Inhye? Okay, if not, we're going to go ahead and move on to Abhishek. Abhishek is a PhD candidate in the in the Department of Geography here at the University of Georgia. And yeah, go ahead, Abhishek. Thank you for presenting with us today.
Let me unmute first. Thank you, Caroline. So my name is Abhishek Kumar, and I am a PhD candidate in Geography Department, and I'm working under Dr. Mishra. So let me share my screen. Okay, can you see my slides? Okay, so this is the work we have published recently in Remote Sensing Journal. So that's what I'm going to present you. Is like, you know, there was a strict lockdown in India, like starting from March to like June, which like created like, you know, some differences in air quality, and that affected the coastal water of India. So how that affected, that's the like, you know, this is study is all about. So what happened, like, you know, like this, like it started 25th March in India, the world's largest and strictest national lockdown that started. And that, like, you know, went into different phases. Like first it was for 21 days, and then it was again for 19 days and so on. And still, like, you know, it's like part of the country is still under lockdown. But here you can see, like in the left side, the picture, you see how the New Delhi was before lockdown. It's one of the most polluted city in the world, like people know about it. But if you see during lockdown, how clear like the air quality became, like, you know, in New Delhi. And same happened in Mumbai, like during lockdown, it was very clean. This is like Juhu Beach, which is like, you know, very populous area, like in Mumbai, which was like also sort like, you know, very like clean air. So what happened is, like, you know, there was massive decline in all urban activities, like industries, like vehicle and public transportation, etc. So that leads to, like, you know, these kind of studies recently like published. So there are like various studies they published. The water quality improved, for example, in Italy. Then there was like water quality in Ganges that improved all over India. So that was the study. If you see in China, there was study about air quality. So it was like before lockdown, like, you know, and after lockdown, how clean the air quality was. And this image you see in the right corner, that was NO2 concentration for India. And that was like, this is for 2019, this is 2020, like during lockdown. So that motivated us to study, because this area you see, this is one of the, like, you know, this area power plant region in this east part of India. This is like world's one of, like, you know, top power plant which produces like greenhouse gas, like, you know, most. So that reduced significantly. So that we thought, like, you know, how that is going to impact the coastal like water, especially in terms of like phytoplankton production. So what happens, like, you know, our hypothesis is like how the phytoplankton get affected. They need, like, you know, some nutrient. So nutrient, from where they get the nutrient, there is like atmospheric deposition that happens or there is like wastewater, comes from like urban runoff or industrial effluent or some agricultural runoff. So there are like various sources of those nutrients that like phytoplanktons need in the water. So which parameters got affected during lockdown mainly is these three parameters you see. One is atmospheric deposition, that is the nitrogen concentration that got like reduced during lockdown. Second is urban runoff that reduced also. Then there is industrial effluent also reduced because industries were like lockdown, there was not operational. So these three sources reduced. So our hypothesis was like, if there is overall decline in this nitrogen input and urban runoff, then that will decrease the phytoplankton biomass in the coastal region. That was our hypothesis. So to test our hypothesis, first we started with nitrogen dioxide concentration, and that data we downloaded like from Sentinel-5P satellite, European Space Agency satellite. So this satellite has like various atmospheric gases. It can measure methane, nitrogen dioxide, and like various other gases. So from those parameters, we were only interested in this nitrogen dioxide. So we masked out like just NO2 tropospheric concentration. And that data is like, daily available data. So if you do daily data, then you can't like find a really good trend. So what we did is we tried to create a monthly mean composite image to see the difference between before lockdown and after lockdown, how much there was a difference. And this is a global data, so we masked out for just India, like applying a country mask, and then created the NO2 composite map. The second parameter we look for is chlorophyll A, that is considered as proxy for phytoplankton biomass. So to derive chlorophyll A concentration, we use Sentinel-3 ocean and land color instrument data. And this data we used during like pre-monsoon condition. So the monsoon starts in India after July. So we like only, analyze the data before the monsoon, because there might be after monsoon, you will see a lot of runoff and nutrients. So that you cannot isolate the effect of lockdown. So we kept that aside. And then you need to do some pre-processing before applying any model to satellite data, because you cannot apply any model directly. There are atmospheric noise and like, other noises you need to remove before that data becomes like, usable. So after doing that atmospheric correction, then we applied some these biooptical models. So what are these bioopticals model is based on machine learning, like, algorithms that was created after like simulating 200 different lakes and the coastal waters around the world. So this is like, the model was developed by Brockman et al., which is available in this software, Snap. So Snap is a free software from European Space Agency. And that's the software we used to derive this chlorophyll A product. And then again, like, once you derive the chlorophyll A data, that is for entire ocean, okay? So you need to mask out for just the coastal water to study the coastal water. So how can you do that? So to do that, we created a threshold looking the, the typical range of the coastal water chlorophyll. And then we masked out like, just the coastal water, and we did not include the clear ocean water. And then again, we created same chlorophyll composite map like NO2 map, and did some zonal statistics like east part of India, then south part of India, and west part of India, like, different coastal region. We did some analysis. The third parameter, which is really important, is nutrient data. But it's really hard to find the nutrient data for developing countries like India, like, you don't get the field data. So in that case, we have like just few data, field data for nutrient from this region. But for other region like western part or southern part, like, the other part, we don't have any field data. So what we did is like we used NASA Giovanni website, where you can derive this nutrient data using some simulated models. So we used this data, and we also used NASA Giovanni to derive precipitation data as well, because that has very strong correlation with runoff, both precipitation and runoff. So here you see the result, so if the first, these two images you see is for NO2 concentration. And in the left side, you see the same month, which was not in lockdown year, 2019 in April. And this is during lockdown, you see in April 2020. And you can clearly see how different, how much NO2 concentration has reduced in all over the part of India. And this is the all over chlorophyll map you see for coastal water of India. This is before lockdown, and this is for during lockdown. And you can clearly see this western part of India, the concentration only, not only concentration reduced, but also the how far this chlorophyll plume was there, that also reduced, like in terms of area and magnitude, both reduced during the lockdown time. And the map you see, this was produced after processing hundreds of Sentinel-2 images. It's not like just one image, it does not cover entire India. So we created a composite in QGIS software, like after processing all the satellite data, we imported it in QGIS and then created this like all over India map. And to zoom in more, so we zoomed in more in the east part, west part, and south part, like different parts of India. You can see this is the which part, east coast of India, how before and after the lockdown concentration, as well as the area difference. And this is the west part of India, and this is southwest and northwest. So mostly we saw the difference in this northwest part, significant difference, and this western part of India. And then we tried to extract also the statistical data, for those 4 different regions. And what you see here, it's a trend, from January to April, pre-monsoon trend. So the black bar you see, that was 2019, and the gray bar you see, this is 2020. So typically what happens, there is an increase pre-monsoon in phytoplankton. Like in April, you will see always a trend, from March to April, there is an increase in chlorophyll A in typical years. But what happened this year, there was a decrease in opposite to the trend. So that was effect. And there is a huge error bars you see here. That is because of we included so many pixels in the analysis from satellite data. That's why the standard deviation you see, it's very high. And this map you see, this is the all India surface runoff map, which shows the nutrient in which part you see. But this the northern part you see is the Himalayan region, so don't worry about that. We were only interested in the eastern part of the India, like this area you see, so you can clearly see in 2020 in the eastern part there is much runoff happening, but there is no changes in the western part or the southern part. Why is that? Because these are the dry month, in India, January, February, March, April, those are really dry month. There is no rainfall during those months. So you don't expect more surface runoff during those months. And here you see the trend for last 20 years for both precipitation and surface runoff. Okay, so what it's showing, if you focus around 2019 and 2020, there was not much change in whether precipitation trend or surface runoff compared to last 20 years. So our assumption, if this runoff is not affecting, the surface runoff is not affecting, then something else might be playing a role. So what could be that? So that is where atmospheric deposition of nutrient comes into play. And this is here, the right side you see is the field data. So we had only few field data, and that also showed significant reduction in NO3 concentration during you see 2020 compared to the regular month like 2018 or 2019. So the nutrient concentration is reducing like, NO3 concentration reduced. So what is like actually why they affected? If the runoff did not reduce, why this will reduce? So that was our assumption, is definitely the atmospheric deposition of nitrogen, playing the role. So in summary, what we saw is like, there is significant reduction we saw in NO2 concentration throughout the country. And the West Coast saw the highest reduction in chlorophyll concentration. And in the long-term surface runoff, we didn't see like, any typical anomalous trend in during lockdown year. And in situ, NO3 data definitely showed significant reduction. And finally, what was our hypothesis was like, that reduction in coastal chlorophyll A could be linked to a net decline in nutrient loading, which is particularly we see like, from nitrogen through water set fluxes and atmospheric deposition. So basically like, the study was about atmospheric deposition of nitrogen, how that is affecting. And it is really hard to find that data, atmospheric deposition of nitrogen. It's kind of like a new field in the research. People, only 2 or 3 studies you can find about atmospheric deposition of nitrogen. And we need to collect, that field data to validate these like results. So these are all kind of preliminary results, but we are like already started collecting some data in India, and we will do some more research in future about this. So if you have any question, I think that's all I have in my presentation, I guess.
Great. Thank you, Abhishek. That was really interesting.
Yeah, I think I took so much time.
Oh no, you're good. We don't have another presenter before our 6 p.m. Next event, and so we're good. We have plenty of time for questions and everything. Does anyone have any questions for Abhishek? If not, I do. So when you were looking at the Sentinel data, what is the frequency of Sentinel, and did you use a monthly mean, or did you do single images for that large area?
Yeah, so Sentinel-3, we use the Sentinel-3 image, so which has the frequency of every day. But the problem is you can't use everyday image because there is a cloud cover, especially in the coastal part. You will find so much cloudy scenes. So we picked up like, only cloud-free scenes for entire month and created the composites. That's why I said like, that image you saw, it's like hundreds of Sentinel-3 images we processed and created that composite.
Got you. And did you have any issues when you're using this higher resolution data in terms of storing data, or like I saw you use Snap? Did you use Google Earth Engine or anything else to make it easier to process all those imagery or all that imagery?
Yeah. I would love to do this in Google Earth Engine, but the problem is in Google Earth Engine right now, Sentinel-3 is not available atmospherically corrected, and they are not providing the metadata. So you cannot correct like by yourself also in Google Earth Engine. So I was stuck with Snap, and it took me like entire my summer I spent on this. Like it was 2 months of work processing those satellite images.
I can imagine.
which I can do just in like 1 or 2 days in Google Earth Engine.
Well, thank you for doing that. The results look fantastic, and you said that they're going for publication soon?
It's published already.
Oh, perfect. Awesome.
Yeah.
Great. Does anybody else have any questions for Abhishek?
Well, I think it's great work. Congratulations, Abhishek. This type of opportunity, it's interesting. It reminds me also of efforts just after September 11th, 2001, when they closed the skies, and works on trying to understand the effects, because airplanes weren't flying anymore. So for a while, you didn't have contrails. So changes in the atmosphere created just because airplanes are flying. In that particular situation, they weren't. So it created a lab or an opportunity for people to go and understand the effects. And COVID, again, does the same thing. creates opportunities for people to study. It's a side effect, I guess, of this whole chaos we are living now.
Yeah.
Very, very true. Awesome. Well, if there are no further questions or comments, we encourage you to stick around. In about 9 minutes or so, we're going to have NASA Develop give their presentation, and then we'll have, after the NASA Develop crew is done, we will have the closing remarks for this GIS Day event. I just wanted to thank everyone, all of our student presenters here, Abhishek, Andrew, and Inhye, and of course, all of our other participants in the sessions that we've had over the last few days celebrating GIS Day here at UGA and this 2020 virtual event. So we really appreciate everyone coming and taking the time to take part in this.